Hello everyone, today I'm gonna go through my diabetes risk prediction project. The goal of this project is to predict whether a person had a diabetes using health and demographic feature. It is a binary classification problem where the target variable is diabetes binary. I will go through my workflow step by step following the exact structures of my Python notebook. So first, in the very beginning of my code, I set up the environment. I imported all necessary libraries like the pandas, NumPy. These are for data manipulations, and the skit learning for modeling, and also the example modules such as the random forest, gradient boosting, the light GBM, and the cat boots. I structured the import carefully so that if certain libraries are not available in the environment, the code won't crash. This makes the notebook more portable and reducible. Next, I load the training and the testing dataset. I built a flexible file path detection logic so the notebook can run smoothly in different environments like the Kaggle or some local machines. After loading the data, I check the shape of both datasets to make sure that everything is correctly read in and the dimension look reasonable. After that, I separate the features and the target variable. I carefully detect and remove any ID column from the feature set because the ID itself has no predictive meaning and could give negatively effects to the model. I also make sure that the training and the testing datasets have aligned columns so that when I generate the prediction later, there are no mismatch. Then I move into the feature engineering. Here I create several intersection features, especially the combination of BMI, the age, the general health, since medically these factors are strongly related to the diabetes risk. These interaction terms allow the model to capture the nonlinear relationship that may not be obviously from individual features alone. I also make sure that the categorical variables are treated properly so that the models can interpret them correctly. After featuring engineering, I perform some basic exploratory dataset analysis. I check for missing value and confirm that the dataset is relatively clean. Then I look at the distribution of the target variables. One important observation is that the dataset is imbalanced. There are fewer positive diabetes cases compared to the negative cases. This imbalance is critical because it directly affects the evaluation metrics like the precision, the record, and especially the F1 score. Next, I explore the feature correlations by generating a correlate metric. This helps me understand which variables are strongly related and whether the multi-collineation might be an issue. It also gives some intuition about the feature might be more predictive. After understanding the data, I define an undefined evaluation framework. Instead of relying only on the accuracy, I computed the precision, record F1 score, and AUC. Since this is an imbalanced classification problem, F1 score is particularly important. I also implement data threshold optimization functions. Instead of using the default probability threshold of 0.5, I search for the threshold that maximizes F1 score on the validation test. This step turns out to be very important for improving the public leaderboard score. Then I start with baseline model. I first test a simple logistic regression model to establish a performance benchmark. I experiment with class weight equal to balanced to address the class imbalance. These adjustments increase recall, which help improve the overall F1 score. After that, I move to tree-based ensemble model like the random forest and the gradient boosting. These models are better capturing the nonlinear relationships and the interactions between variables. Again, I apply this threshold, turning to maximize F1 score instead of sticking to the default threshold. Then I experiment with PCA combined with logistic regression. The idea here is to reduce the dimensionality while preserving most of the variance. I return about 95% of the information and retain the classifier. While this approach improves model stability, its performance is slightly lower compared to a tree-based model. I also tried a neutral network model use an MPL classifier. I apply feature scaling and design a two-layer hidden structures. Although the neutral network are powerful, in this structured tabular dataset, they don't outperform ensemble tree models. After comparing the individual models, I analyze feature importance using a method like the random forest, feature importance, and permutation importance. This helps identify the most influential predictors such as BMI, age, and the general health. Then I move to stronger boosting models like Light GBM. I incorporate the cross validations and compute the scale post weight to better handle the class imbalance. I generate out-of-fold predictions to obtain a more stable estimation of performance. Finally, I experiment with model blending. I combine the prediction from multiple strong models to reduce variance and improve the generalization. After identifying the optimal probability threshold, I generate the final predictions for the test set and save both binary label and predicted probability. Overall, this project follows a complete machine learning pipeline. The data processing, the feature engineering, model benchmarking, the threshold optimization, and the ensemble modelings. The key importance came from handling class imbalance properly, optimizing the classification threshold, and the leverage strong ensemble method with cross-validation. Thank you for watching.